Bismillah ar-Rahman rahim Assalamu alaikum. Okay, so today we are going to talk about these particular things. We'll start with a discussion of data types and why it is important to know about these different data types that MATLAB or Octave supports. In the beginning, in our very early lectures, we have talked about these data types. Like we have looked at how integers are stored, how text or characters are stored in a computer, and how real values are stored inside a computer. And they're all different methods. Okay, so integers are encoded differently. Real values are encoded differently. We have talked about the IEEE 754 notation, in which single precision and double precision values, they are encoded differently. So I hope you remember that. And similarly, we have talked about the encoding of text. We have talked about ASCII. So whenever you type in text or whenever you store text, so it is stored differently. So that's why we have these different data types for storing different types of data. And it is important that you know about these data types and you know about their limitations. You have some idea about their limitations and all that. Then we have learned how to create vectors and matrices. Today we are going to see like how can we access data stored in those vectors and matrices. We will learn how to access individual elements of a vector and a matrix, and how to access different slices of a vector or a matrix, okay, or how to access different rows or column vectors inside a matrix, and accessing multiple rows or multiple columns and all these things. We have talked about multiplication, exponentiation, subtraction, divisions, and all these things. Today we are going to look at element-wise operations, arithmetic operations, okay? So we'll see what is the difference between normal multiplication of two vectors and the element-wise multiplication of two vectors. And similarly, we look at the exponentiation, element-wise exponentiation of vectors and matrices. Moreover, we did talk about this particular relational operator equality when we were talking about the assignment operator. So we talked about this relational operator equality. There are other relational operators available in Octave or MATLAB, which you can use to determine the relation between two values. The values can be two scalar values, or they can be vectors or matrices. So you can use these relational operators to determine the relationship between two variables. Okay. So by relationship, we mean whether one value or one variable is smaller than the other, or greater than the other, or smaller than or equal to the other, something like that. And then we'll also see how we can use script files for programming. So this is the outline for today's lecture. Let's get started. We'll quickly go through this material. We have talked about it. We are not going to go into a lot of details. Uh, you can go through it later on. I hope like you have went through these slides, because I have uploaded these quite early. So these are the available data types in Octave or MATLAB. We have the double data type, and this is the default data type. Any numeric value that you create or store in MATLAB or Octave, it is stored as a double value. Now a double value uses 64 bits, and it uses the 64-bit double precision floating point format. We have discussed this one in detail, the single precision format, that's why it's called single. And we have learned how to encode a number into this format, okay? Now both these values, these are the ranges of values that you can store. So you can store this very large negative value, minus 1.797 multiplied by 10 raised to the power 308. So this is a very large negative value. And this is a very small negative value, minus 4.94 multiplied by 10 raised to the power minus 324. So this is a very small negative value. Now this is a very small positive value, 4.94 into 10 raised to the power minus 324, and 1.79 into 10 raised to the power 308. So this is a very large positive value. So these are the range of values that you can store in double. Similarly, in single, you have relatively smaller ranges. Double variable isn't just called double because of its higher range of values, but because of its double precision. So you can have more precise data stored in it. So you have here more digits after the decimal point, and here in the case of single, you have fewer digits after the decimal point. Okay, so these are around 6, 7 digits, and here you have around 15 or 16 digits, most probably, something like that. Similarly, we have other data types. We have a 32-bit integer, which can store 32-bit signed and unsigned values. The range is -2 billion to +2 billion. We have unsigned 32-bit integer. It can store values from 0 to 4 billion. So I hope you know how does that happen. Like you know how can you get this range? 16-bit integer you can store, and its range is very small, -32,000 to 32,000. One might wonder, why do we have these data types? Okay, so as MATLAB or Octave is like it is used to work with different types of data. So these types of data types, like the unsigned integer, 8-bit unsigned integer, or the 16-bit unsigned integer, or the 32-bit unsigned integer. So these types of data types, they are mostly used when you're working with images, when you're storing color information and all that. So they happen there. So you can use these data types. But by default, any variable that you create, it is of type double. Okay. You also have the character data type, which is not mentioned here, but the character data type is kind of an unsigned 8-bit integer value. Okay, so its range is from 0 to 255. Okay, so these are the numeric data types that you are available with. Okay, of these numeric data types, these are the integer data types, and the integer data types uh, they are they are quite useful for integers, but they have a small range. Like the maximum that you can work is with +4 billion. So it might turn out to be a quite a small value, and you may need to go and shift to the double data type. Okay, but as long as you are within this range, so you can use these integer data types. Nevertheless, as I mentioned earlier, these data types are used mostly when you're working with image data. So image data is mostly it is stored in the integer format. Other than that, any other numerical computation usually requires that you move on to the double precision value. Floating data point. So we've talked about this floating data point in detail, and we have looked in pretty much a lot of detail at the format in which these single or double precision values are stored. So these values are used for storing decimal values or real values, non-integer values, and very rarely would you use the single precision value. Mostly you would go by the default data type, and that is double. So mostly you would be working with double values. Uh, Okay, why should you care about data types? Now, it's always a very common assumption among people who are new to computing that perhaps computers are very powerful machines, and which they are in a certain way, but nevertheless they have certain limitations. And computer devices, being digital devices, they have finite amount of resources. So they have finite amount of RAM to store data, and they have a finite amount of computational power. They can achieve a finite amount of precision. Okay, so with limited amount of bits to store the data, for example, even if you are using double precision data type, so a double precision value can be stored in 64 bits. So 64 bits, although it's quite a huge amount of bits, a huge number of bits, but still it is 64 bits. It is a finite number, and there are numbers that cannot be stored precisely within those 54 the 664 bits. Okay, so we will look at this one example, and you will see the limitations of this thing. For example, if we have, say for example, a equal to 4 by 3, like if you perform these calculations normally using a piece of paper and a pen. So say a is 4 by 3, and next we assign the value a minus 1 to the variable b. So if you do a minus 1, which is 4 by 3 minus 1, so what you'll get is 1 by 3. Okay, so what you'll get is 1 by 3. Okay, so 4 by 3 is basically 1 whole, 1 by 3. So you subtract the 1 whole, so you get 1 by 3. So that is, so technically B should have the value 1 by 3. Now C is B times 3. So basically you're trying to cancel out the 3. So C should have 1. And E should have the value 0. Why? Because C should have 1 and E is 1 minus 1, so it should be 0. So technically E should have the value 0. But that is not what happens. E does have some non-zero value. Now, why does it have a non-zero value? It happens because the computer cannot store 4 by 3 or 1 by 3 uh, very precisely. Okay, so there is always some round of error, some truncation error and round of error, and because of that error, you get this result where E is basically a non-zero value, whereas it should have been a zero value. So let's see, like, what does Octave do? So let's say we have A equal to 4 by 3. So I'm going to suppress the output, 4 by 3. And then we have B, and B is equal to 4 by 3 minus 1, A minus 1. Okay, A minus 1. Okay, that is B. And then we have C, which is equal to B multiplied by 3. And then we have E, which is 1 minus C. And ideally, we would expect that this should be a zero value, but it is not zero value. It is a very small value, but it is some value. E is not exactly non-zero. Okay. So why does this happen? It happens because although you're using double precision format, uh, but still, because of the way computers store numbers and because of the inherent limitations of that notation that computers use, so there's always going to be situations where you will have errors like these. Okay, so the computer is not going to uh, do something that is very like foolproof. For example, if we have a is equal to uh, 1 divided by 3 and say multiplied by 3. So in this case we are getting 1, but let's say a is equal to 1 by 3, sorry, and b is equal to a times 3. Okay, we are still getting 1 here, but if you go and follow this sequence of instructions, you get to like you get to a situation where you should have had a zero value in this particular variable e, but you do not end up with this value. Now, why does this happen? It happens because computers are inherently limited in their capacity to represent or store numbers to the ultimate precision. Okay, so there is always going to be numbers. Those numbers are going to be real numbers. Those numbers are going to be rational numbers. Okay, not irrational numbers. But those numbers are going to be rational numbers with recurring decimal representation. And if you have a rational number with non-terminating recurring decimal representation, so if you try to store it in a computer, you have to truncate the non-recurring sequence of decimals. And when you do that truncation, so that truncation introduces a small amount of error in the value that you store in your computer. Okay, and that error can accumulate over subsequent uh, calculations. So you should be aware that even double precision representation like double precision, it is inherently finite and it is inherently limited. Okay, so this is how Octave does these calculations. Uh, and the moral of all these calculations is that it is not possible to perfectly represent a real number using a finite number of ones and zeros, and that is what we have been talking about. No matter what you do, there's always going to be a situation where you will have numbers that you won't be able to represent perfectly in those 64 bits. So not all numbers can be represented exactly even using 64-bit doubles. If we do many calculations with numbers that are just a tiny bit off, that error can grow significantly large depending on the type of computations being performed. Okay, so depending upon the type of computations that you perform, uh, we can have a huge amount of error by the end we are done with those calculations. So whenever you're using computers, so you should be mindful of the limitations of computers. So computers do make errors, and those errors can accumulate over time, and they can become very big and significant if we do not address those errors in time. Okay. Similarly, although the double has a very huge range, like double has a very huge range, but still double, despite its very huge range, like it has some limitations. For example, like you may come across values that are too big to even fit in a double data type. For example, we have these two calculations here. A is equal to 380 raised to the power 1500. Let's do that. Say we say A is equal to 380 raised to the power 1500. Okay. So it says A is equal to infinite. INF stands for infinite. So A is such a huge number. This computation results in such a huge number that it cannot be stored in a double. Okay, this is one thing. Next, say we say B is equal to factorial. Say, do we have factorial as a function? Let's try factorial as a built-in function. Factorial of 5. So it should be 120. Yes, we have a factorial function that is built into Octave, so you can call it to find the factorial of any number. So if you go try bigger numbers, say factorial of 100, let's see if it can find it. Yes, it does. Factorial of 150. Yes, it does. Okay. Factorial of 160. Yes, it does. 170. Yes. 175, say. Infinite. So the factorial of 175 is infinite. Now, factorial is a function that you might use more often than any other function. Maybe, like there may be situations where you would like to find out the factorial of some number, and 175 is not that big a number. So if you try to find the factorial of 175, your computer may not be able to handle that number. Okay, using the built-in data type, the double data type that it has, it may not be able to do so. So what should you do in those situations? The first thing that you should do is you should be aware of these possibilities. These are real possibilities that can occur, and you can come across numbers that may not fit into the data types that you're using. Then what should you do? You should go for bigger data types. Okay, so some tools, they may provide you with those bigger data types, or you might need to write your own code to create those data types and then work with them. Okay. So the point that I want to make here is that you should be aware of these possibilities, that you can have situations in which you may end up with values that are too big to handle. Okay. Let us clear the command window and let us clear the workspace of all these variables. Okay. Let's see what do we have here next. So I guess this is similarly the ASCII code. We have gone through this. The ASCII code of capital A, small a, we have talked about it in detail. When you store text inside your computer, so it is stored as ASCII code. Okay, so you can store strings in Octave. We have done that yesterday, and those strings are stored as characters. Okay, so and although each ASCII code, like, it takes a single byte, but sometimes I guess Octave stores each letter in 2 bytes maybe. Okay, so that may change, but it is not that important right now. We can verify it. For example, let's see, we have a variable a, and a stores a string. Okay, so say a stores this is, or a stores a itself. Okay, so a is equal to a, and let's use this function whos to find out all the variables in the workspace at the moment. So it uses single byte. Okay, so Octave uses a single byte to store a character. So a will have the ASCII code. A will have the ASCII code. Okay, so we can have another variable, say b, and we can say b is equal to a plus 1. Okay, so now b is equal to 98. That means a was equal to 97. So 97 was the value stored in a, and 97 is the ASCII code of small a. 97 is the ASCII code of small a. Okay, so you can store strings. Uh, you can store strings in Octave, and those strings would be arrays of characters. Each character would take a single byte, and the string would take the number of characters multiplied by that 1 byte. That many bytes it would take. Okay. Okay, so we have talked about this term arrays. You can think of an array as something arranged in a single row or in a single column. You can think of an array as a कतार. ठीक है, array को आप सोच सकते हैं कि ये एक कतार, इसकी मिसाल एक कतार की है. ठीक है. So why do you need arrays? We need arrays if we want to store similar data. For example, if I have to store the marks obtained by a single student, so I need one scalar value. ठीक है, मुझे I need one double variable to store those marks. But if I need to store the marks of the entire class, and the class has say 45 students, so I need 45 variables. Okay, so it is difficult to have 45 different variables. It is easier to have an array with 45 different elements. Okay, so that array can be one dimensional. And if I want to have to store the marks of all those students in 5 subjects, so I need to have a multi-dimensional array which has say 45 rows and 5 columns. Each column will store the marks of students in one subject, in a single subject. Okay, and each row will basically store the marks of a single student in all 5 subjects. So you can think of it like that. So that would be a two-dimensional array with rows and columns. Okay, you can think of it as a matrix. So a matrix is basically, so we have basically a two-dimensional array. So we have done this plotting. Let's get back to the next item on the agenda, and that is we need to talk about how to access data in vectors. Okay, so this is important. You should pay careful attention to it. Some of the videos on the playlist, they deal with this thing. I hope some of you or most of you have gone through that. So let's get started. So pay very close, be very careful and pay close attention to what I do here. So I will be basically whatever we have learned so far, I'll be repeating that in many ways. And so yesterday we talked about creating vectors. So today we are going to do the same, and we are going to combine different ideas. For example, let me create a vector A. Okay, so we are going to create a vector A. So how did we create vectors? So we learned about different techniques. One was you specify all the elements, like you do this 2, -1, 0. So this was one way. Okay, so we have done that. Yesterday we talked about the linear space function, lin space function, and we created vectors by comprehension. We used the colon operator. Okay, so you can mix these two approaches. So let us do that. For example, let us mix the two approaches. Let us use that comprehension approach. So I want this vector to have a range of values starting from 1 with a step size of 2, and then ending at 6. Okay, it will not end at 6, it will end at 5. So we'll have 1, 3, 5. Then if we add 2 more, it will become 7. So 7 goes out of this range. So we'll have 1, 3, and 5, and then minus 1 and 0. So this will be the vector. Okay, so it will have 5. It will be a row vector with 5 entries. And the first 3 entries, 1, 3, 5, these entries are generated by this thing. Okay, so this is the initial value 1, this is the step size 2, this is the final value 6. Now the values that we get, it may contain the final value and may not contain. Okay, why? Because the starting value determines like what should be the final starting value, and the increment size that determines what should be the final value. So the starting value is 1 and the increment is 2. So 1 plus 2, 3 plus 2, 5. If we add 2 more, it becomes 7, which goes out of the range. So 7 is not added to this vector, and we just like we stop it stops at 5. So 1, 3, 5, and then minus 1, 0. So this is how this is also like a combination method of creating a combo method of creating a vector. Okay, so we are using those two methods. Now, if you want to access individual elements of this vector, for example, I want to access this element. Okay, so how can I access this element? Or if I want to access this element, or if I want to access this element, or if I want to access this element, how can we do that? Now, A is a vector with 5 columns, 1 row and 5 columns. Okay, so if you want to access, and it is a row vector, it is a row vector. Even if it were a column vector, so for example, let us have B. Let us create B, and let us say B would be a column vector, and we want to create the column vector from A. Okay, so this is A, and then we add this single quote. So this means A transpose. This means A transpose. So the transpose of A would be determined. So that would be a column vector. Transpose turns a row vector into a column vector. Okay, so B would be a column vector. It would have the same entries, but it would be a column vector. Why? Because B is equal to A transpose. Okay. Okay. So say for example, we want to access individual element inside a vector. If you how can you do that? Like this is a vector with multiple values, or this is a one-dimensional array with multiple values. Okay, so how can you access individual elements, individual values? Okay, so think of it as consider the analogy of your class. So in your class is, say for example, industrial engineering, first semester industrial engineering geology. So this is, say, the name of your class, and inside your class there are, say, 45 students, say for example, or 50 students. So how do we access each individual student in the class? So of course it is difficult to remember the names of all the students, they are all unique. So the easier way is that every student is assigned a class number. Okay, and the class numbers, they always start from 1 and they go up until the size of the class, say 45. So starting from 1 to up until 45. Exactly the same way, the same thing happens here. So we have this vector A, or we have this one-dimensional array A, and this one-dimensional array has these 5 elements. Okay, now how do we access these 5 elements? So in order to access these 5 elements, we use something similar to the class number, something similar to your class number. Similarity is, it is a number, it is an integer value, it starts from 1, it goes up until the size of the class. Okay, so in this particular vector A, that class number would start from 1, then 2, 3, 4, 5, and 5 is the size of this array. So it will go up until the size or length of this vector. Okay, so it will start from 1, it will go up until the length of this vector, which is 5. But we don't call it class number, we call it as the index. We call it the index. So we use the index to access individual elements in a vector. Okay, so let me add this term index. So we use index. Index is similar to your class number. Okay, so in order to access individual elements in a vector, we use the index. Index always starts from 1 and it goes up until the length of uh, the vector. So let me specify the range as well. So index, it always starts from 1. Say index range is from 1 to length of the vector. That is the range of index. Okay. So if you want to access a particular element, so if you want to access this element, so it is at index 2. So how can you do that? You can say a element of a at index 2. You specify the index within parentheses. Element of a at index 2. What should we do? Just display it. Okay, so it is 3. So what is the element of a at index 4? It is -1. -1 is at index 4. What is the element of a at index 5? It is 0. What is the element of a at index 6? This is an illegal index, out of bound. Okay, so it is beyond 5. So there is nothing beyond the index 5. Okay, this is how it works. If you want to access individual elements of a vector, so you need to use the index, and you do not just access it like you cannot just access it for printing. You can do anything with it. For example, this is the index at 5. If I want to increment this index, or if I want to change it, say for example we want to change it, we want to change a5. How? So we want to access f5 and assign it a new value. So what is that new value going to be? It can be anything. It can be just this value 6, say if you like 6. So now a becomes 135 minus 1 6. Okay, so we have changed this value. Or it can be anything else. For example, it can be, say, the sum of a4 and a5. Okay, so it can be any value. Okay, so a4 and a5. So this is a4, this is a5, -1 plus 6, so you get 5. It can be this thing. Or you can do something like this. For example, we want to say, for example, we want to increment this value a3. Okay, so you can use the increment operator. So increment is also a numeric operator available in MATLAB or Octave. So you can say increment, the double plus sign. Okay, so this will increment. What do you want to increment? We want to increment this particular value a3. Okay, so read it. You should be careful. Like this is, we want to access the third element of a, vector a. So you first write the name of the vector a, and then within parentheses you specify the index or the class number of the element. Okay, so this 3 is not this 3. It's not a value. It's an index. So in vector A, you start from the first 1, 2, 3. This is what we mean by this A3. This is what A3 means. Okay, so we want to access this element and we want to increment it. Okay, so you can increment it. It becomes 6. A3 becomes 6. And what does A become? So A becomes 1, 3, 6 minus 1, 5. Now after that, incrementation. So this is increment. We also have this decrement operator. Say for example, we want to decrement -1 further. Okay, it is already -1. We want to decrement it. So -1 is basically a4. We want to decrement. So you press the negative sign 2 times. So we want to decrement a4. The fourth element of a, we want to decrement it. This is the fourth element of a. Okay, we want to decrement it. So decrement it. Fine, no problem. So this is what A becomes then. 136 minus 2, 5. This is what A becomes then. Okay. Okay, I hope you are following it. Similarly, you can do the same thing to a column vector. B is a column vector. Okay. If you want to access any element of B, you can use the index. Index starts from 1 for the first element and it goes up until the length of B, which is 5 in this case, and which is this element. Say, for example, we want to access the fifth element of A. So you can do that, B5. It is 0. We want to change it, say, for example. So we want to decrement it so that it becomes negative. So we want to decrement B5. You can do that. And let's print B then. So it becomes 1, 3, 5 minus 1 minus 1. So you can do that. Okay, this is fairly easy. Okay. Similarly, you can access any other element. For example, B2. So we want to say modify B2. So what do we need? What do we want to do with B2? So we want to say B2. We want to replace it with B3. So you want to say B2 is equal to B3. We want to replace it with the value at the third index. So now we have copied B3 into B2. So 155 minus 1 minus 1. This is what it becomes. Okay. So I hope this is you're following it and it's not that difficult for you to follow. Okay, let us clear the command window. Let us look at B again. Now we have learned how we can access individual elements in a vector or a one-dimensional array. The vector can be a row vector or a column vector, doesn't matter. What if you want to access multiple values? Okay, what if you want to access multiple values? Now multiple values can be a range of values. For example, if you want to access the values from index number 2 to index number 4, how can we do that? So we can do it like this. We can say B and get us the elements of B from index number 2 to index number 4. Okay, and the step size is 1. You can specify the step size or you can just ignore it. You can use the default step size, which is 1. So what would this do? What are we telling Octave to do? We are telling Octave that we want to access something in the vector B. What do we want to access? We want to access the values that are stored at index number 2 to 4. Okay, so 2, 3, and 4, those values stored at indexes 2, 3, and 4, that will be fetched. What are those values? 5, 5 minus 1. So that is what you're going to get. In fact, you can construct a new vector from these values. You can say C is equal to, C is a new vector, and we want to construct C by taking a slice out of B. So we want to take a slice out of B, this slice. This is also called slicing. This operation is also called slicing. So we are taking a slice out of B, this particular slice, 2 to 4. Okay, so we want to do that. Okay, you can do that. So we have a new column vector C, and C has been constructed by taking a slice out of B. Okay, now we can take a different slice as well. So let us create another column vector D, and D would be constructed by taking elements out of A, starting from 1 and then step size of 2 and going up until 5. Okay, so now this slice is going to be a bit like not exactly a continuous slice, but pieces of B put together into a slice. Okay, so we will get 1, 5, minus 1. So D will have 1 because the starting index is 1. Then we have a step size of 2. So the next would be 3, and after 3, 5, and then 7. But 7 is not good. It's going to get out of range, so we are not going to get 7. So we are going to get elements at index number 1, 3, and 5, which are these elements 1, 3, and 5, index 5. So 1, 5, and minus 1. So you press enter, you get D. D is 1, 5, and minus 1. Okay, so you can do something like this. Okay. Fine. So I hope like this is clear. And this equally applies to the row vector A as well. You can do the same thing to A as well. Okay, no problem with that. So we have constructed these vectors C and D by taking a continuous slice out of the vector B and by taking different pieces out of the vector B. Similarly, you can do something else as well. Let me clear the command window. This is our vector B. Uh, you can construct another vector, say, for example, uh, let us call that vector V, and you can construct this vector V by providing the indexes of elements that you want to have. Okay, explicitly providing those indexes instead of providing a range like 2 to 4 or 1 to 5, step size 2. Instead of that, you can do something like this. Say, for example, uh, so when you say something like this, B and then parenthesis, that means that you want to access elements of B. Now, which elements of B? So you can put a single value. If you say 1, so that means element of B at index 1. Or you can specify multiple indexes. Okay, so how do you specify multiple indexes? So you then use square brackets. So you can say I want element at index number, say 1, 4, and then 5. So these indexes do not have a particular sequence. So you here you specify that you want element stored at index number 1, 4, and 5, and you want these elements to be put together to construct the vector V. So you can do something like that. If you do that, this is what you're going to get. Vector V would have these elements 1, minus 1, minus 1. Okay, so you can get these values like that. So this is how you access elements inside a vector. Okay, so this is important. Like you should know how to do it, how to access individual elements, how to access multiple elements. Those multiple elements can be in a continuous range or slice. They can be at different locations. So you can do all these things. Okay. So this was the first part. So we learned how to access individual elements in a vector. You should know what an index is. It always starts from 1 and it goes up until the length of the vector. Okay, so that is how it varies. And you can we learned how to access a slice of a vector. In fact, not just a continuous slice, but different chunks of the vector. Okay, so we learned how to do that. Now the same thing, more or less, with some modification, applies to matrices as well. Okay, the same thing applies to matrices as well. So let us do that. Mm, let us clear the command window and let me clear the workspace. I want to get rid of all these variables. Let us generate a matrix, say M1, and let us generate the matrix M1 using the randi function. Okay, so we want to generate a matrix with random values, and those random values are random integer values. So what were the things that you specified? So the first thing you specified was the maximum value from 1 to what value. So we want these values to be in the range of 1 to say 9. Okay, and then what is the order of the matrix that we want? Say we want a matrix of order 4 by 4. Okay, so this is M1. M1 is a matrix of order 4 by 4 with random integer values in the range 1 to 9. Okay, this is what we have. Now, if you want to access individual elements in this matrix, so what are you going to do? The same thing. Now, a matrix is a two-dimensional array. So it has rows and it has columns. So if you want to access individual element, you have to specify the row index and the column index, like in which particular row is this element located and in which particular column is this element located. Say, for example, we want to access element, we want to know which element is in the third row and second column. Okay, so this is the third row, row number 1, 2, 3, and column number 1, 2. So this is the element in the third row and second column. When you do that, so 3 will be printed. And you can change it like exactly the same way. If you want to assign it a new value, you can do that. You can say 3 is equal to, say, for example, 0. So M32, sorry, M132 is equal to 0. So you can change it, or you can apply the same operation. Like you can say uh, again, uh, let us learn something new. So you can say M132 plus plus. Okay, so we want to increment this variable, this value. Okay, no, it didn't work. Okay, this doesn't work in the post increment format. Let's see if it works here. Plus plus M132. Why? It became 1. Sorry. Okay. So let's see what is M1 right now. Mhm. So M1 is 2. That means this increment worked, but this answer was not updated. Okay, so it works. The post increment works. Like post increment means this is the increment operator. It is unary operator. So you can put it before the operand. This is called pre-increment. You can put it after the operand. This is called post-increment. So it works either way. And why did we get this answer here? It also makes sense. It's not incorrect. This is very much correct. It is post-increment. So you are the value. This value is displayed first and then incremented later. Okay. So it is displayed, the old value is displayed, and then after displaying the old value, it is incremented. Okay, so it works like this as well. So the point that we wanted to demonstrate was that you can access. Let us clear the command window. This is M1. So we incremented this value. Okay, we incremented this value. Similarly, you can work with another value. Say, for example, this is 9, and we can decrement this value. Which particular value? The value in second row and first column. So M21, we want to decrement it. Okay, and then I'm putting a semicolon here, so you won't see anything on display, but it would be decremented. Okay, so it would become 8 then. If you print M1, okay, so now it is 8. So we decremented this value. So you can access any value in this matrix. Just provide the row index and the column index. For example, this value. Okay, so this is in row number 2, column number 3. So if you want to access it and change it, you can do that. So M1, which value in M1 do we want to access? We want to access the value in row number 2 and column number 3. And what do you want to do with that value? Say we want to decrement that value. Okay, so we want to decrement that value. So you can do that. You can decrement it. Okay, so it will be decremented. It will become 0. So the next time you print M1 or display M1, so this value at row index 2 and column index 3, it will be 0. Okay, now this is fairly simple. Like I guess you have some idea of these things from your background in linear algebra or matrices in your FSC and in your matriculation. So this is simple. In order to access any element, you need to provide the row and column indexes. Okay, so now you have to work with two indexes because you have two dimensions, rows and columns. If you have three dimensions, a three-dimensional matrix or three-dimensional, it's not called a matrix then. You have to call it something else. I guess it can be called a tensor or something like that. But a three-dimensional array, then if you have elements in a three-dimensional array, then you will need three indexes. Okay, so one for the x-axis, the y-axis, and the z-axis. So as soon as the number of dimension increases, you will have more indexes here. So let us restrict ourselves to two dimensions for the time being, and let us try to learn these other things. Okay, Now, for example, so I hope like you have learned how to access individual elements in a matrix. You know how to do that. And whenever we say access, you can, by access we mean you can read it and you can change it. You can do operations on it. You can assign it a new value. You can increment it, decrement it, post increment it, pre-increment it, post decrement it, decrement it. Okay, so you can do all sorts of things with it. Now let us learn how to access individual rows. Say for example, we want to access this full row, the second row. So what can we do with that? Say for example, I want to construct a vector R1, R say R1. So R1 is, or R2 is the, say, the second row of this matrix. Okay, so I want to access it. How can we do that? So again, it's easy. So you need to say, you need to access the second row of uh, M1. Okay, so you specify the row index 2 here, and you specify the full column here. So that means all columns. This would mean all columns. Okay, so you want all columns in the second row. That means you want the complete second row, and you want to assign it to R2. Okay, so you can do that. So now we have accessed the complete second row. We have accessed the complete second row. Similarly, you can access any other row. You can say I want the complete fourth row. Okay, so you can get the complete fourth row. That you can do. If you want a column, say you want the third column, say for example, so how can you do that? So you say I want the third column, all rows in the third column. Okay, so then you get the third column, all rows in the third column. Okay, so let us clear the command window. This is M1 and this is C3. C3 is basically the third column in M1. C3 is the third column in M1, and we have accessed the third column in M1. So this is how you can do it. You can access any other column. Say you want to access, or you want to do something like this. You want to add two columns. Okay, so you want to do this thing. C3 is equal to, say, the first column of M1. So all rows in the first column, sorry, plus the fourth column. Okay, so if you need to do something like this, you can do it this way. So we want to construct a new column vector, which is basically the sum of the first column of M1 and the fourth column of M1. Okay, or maybe you can do subtraction. That will give us more interesting values. So this is what we want. You can do that. So let's see what C3 would be. So C3 would be the first column minus the fourth column. Okay, so 9 minus 9, 0, 8 minus 3, 5, 6 minus 6, 0, 2 minus 3 minus 1. Okay, so 0, 5, 0 minus 1. That is what you get. So this is how you can access individual rows and individual columns. And you can operate on those rows and columns. Okay, no problem with that. You can do that directly here. Okay. Okay. Now, what's next on the agenda? So we've learned how to access individual elements in a matrix, how to access individual rows and individual columns. The next would be, how can we access submatrices? How can we access submatrices? So say for example, let me clear the command window. This is, say, M1, the matrix. Say for example, we want to access this submatrix. Okay, this one, 6024. 6024. We want to access this thing. So let us call this is submatrix, SM. Okay, and SM, and we want to access this submatrix, which runs from rows number 2 to 3 and columns number 2 to 3. Okay, so we want to access this thing. So we want to access a submatrix inside M1, where the row indexes, they run from 2 to 3, and the column indexes, they also run from 2 to 3. Okay, enter. So you get this submatrix 6024. Easy. Okay. Say for example, let us try another one. Say we want this submatrix 0346 0346. So if you want this one, so what are the row indexes? 2 3. What are the column indexes? 3 4. Okay. So you can say the row indexes are 2 3 and the column indexes are 3 4. 3 to 4. 3 to 4. So you get this submatrix 0346. Okay. Okay, this is also easy. I hope like you find it easy. You can get any other, like look at this matrix and select whatever you want to select and we can get it. For example, if you want to get this one or say this one, 6229, okay, 6229, this submatrix. So the row index, it runs from 3 to 4, the column 1 to 2. So it's fairly simple. 3 to 4, 3 to 4, and 1 to 2. Those are the column indexes. Okay. Okay, so if you press enter here, so you are going to get this submatrix. Which one? This one that we selected, 6229. 6229. Okay, you can get this one. Now, these are submatrices where like the row indexes and column indexes, they like are in a sequence. You can choose any other submatrix. For example, you want this submatrix 9 9 2 3. So you want all the corner elements. Okay, so you can get that as well. So what are the elements that we want? Say for example, let us try to get that. uh, Sub matrix is equal to M1. So which elements do we want? So we want these elements, elements with row indexes 1 and 4. Okay, row indexes 1 and 4. So now these indexes are not in a series, they are just 1 and 4. So how do you specify? So you specify it using the square brackets 1 and 4. Okay, we want these elements as these row indexes, and which column indexes? So column indexes are also 1 and 4. 1 and 4. Okay, so hopefully we'll get 9923. So SM is equal to 9923. Similarly, if you want some other like elements, say for example, you want these elements 6 3 9 3. Say for example. So how can you get this one? So in this particular case, 6 and 6 3 9 3. So we have row number 2 and row number 4. Okay, so 2 4, and column number 2 and 4. Again they are the same, column number 2 and 4. Okay, so you're going to get 6393 6393. Okay, now you can not just access these elements, like you can change these elements as well. Say for example, this is matrix M1. Okay, and I want to change these elements, say 6 3 9 3. I want to replace these elements. So how can we do that? So M1 is equal to M1 2 4 2 4. This will give me access to these elements 6 3 9 3, and I want to replace it with something. So, okay, so this will be a 2 by 2 matrix. So I want to replace it with an identity matrix of size 2 by 2. So I want to say, like, I want to replace 6 3 9 3 with 1 0 0 1. So this is how you can do it. So if you do that, so 6 is replaced by 1 3 by 0, 9 by 0 and this 3 by 1. So we have accomplished that. Okay. So again, this is a powerful method of accessing the different parts of the a matrix, a two-dimensional array. So you can use these techniques. So I hope like I have covered almost all of this. So we know how to access a row vector, a column vector. We know how to access. You can access multiple rows as well, multiple columns as well, or you can access sub matrices. So accessing sub matrices. So we have learned about that as well. Now rows and columns, that is very easy. Multiple rows and multiple columns. If I haven't covered it already, so let me do that. So this is M1, and say if you want to have just these two rows of M1 in a submatrix. Okay, so you want a submatrix to have just two row vectors of M1. So which row vectors do we want? Say we want row vector number 1 and 4. 1 and 4. We want just these row vectors and all the column entries. So this is fairly easy. Like you will have SM, and SM will be just the first and fourth row. Okay, or you can have SM and it will be all the rows and just a couple of columns. Say for example we want the second and third column, or second and fourth column, 2 and 4, second and fourth column. Okay, so we will have a submatrix with this column 8120 and 9061. So you can have it. So 8120, 9061. So you can do that. Okay, so this is fairly easy. Like you can try it on any matrix. You should know like how this works. These are powerful techniques that if you know and if you have mastered, so they will make your life very easy in dealing with more complex problems. Okay, if you're trying to solve something more complex using MATLAB or Octave, so you will be able to do that fairly easily. Okay, so I guess we are done with this thing. Okay, so this is done, and this is very interesting. It can be very tricky, and you need to master it. Okay, so I hope like you're paying attention and you're learning these things. The next thing that I want to emphasize, not emphasize, but I want to point out or highlight is that like we have tried multiplication. Okay, so we have done that. So let me clear this command window and let me clear the workspace as well. Let us create these variables, these vectors, row vector and say row 1 and column 1. So we have, say, let us create two row vectors. So this is 1, 2, 3, 4. So this is one row vector. Let us have another row vector, R2. And let's say R2 is 1, 0, 0, 5. Say, for example, this is R2. Okay. Now we know that R1 and R2 cannot be multiplied. These are two row vectors. Okay. R1 and R2, you cannot multiply them. They are not compatible for multiplication. Okay, so this multiplication, if you're multiplying two vectors, basically you're trying to find their dot product or scalar product. That's why, so you cannot find the scalar product of two row vectors or two column vectors. Okay, so you can always multiply a row vector with a column vector. Okay, so you can multiply these two if you find the, if you can multiply R1 with the transpose of R2. Now R2 is a row vector. When you take its transpose, it becomes a column vector. So you can do this multiplication. This is fine. This is conformant. Okay, so you get 21. So R1 multiplied by R2. Okay, so the column vector R2 transpose. Okay, so R2 is a row vector, but if you find its transpose, it becomes a column vector, and you can do this multiplication. This would be a dot product then. Okay, so what does this dot product give you? It gives you a single scalar value. That's why it's called scalar or dot product. and you know how to do that. Okay, so 1 ones are 1, plus 2 zeros are 0, plus 3 zeros 0, plus 4 fives are 20. So 1 plus 20 is 21. Now there is another multiplication that is possible. Like we cannot do this thing R1 multiplied by R2, but we can do element-wise multiplication. Element-wise multiplication means we multiply just the corresponding elements of these two vectors R1 and R2. Okay, so just the corresponding elements of these vectors. So how can you do that? So in order to do element-wise uh, operation, you just add this period, full stop का जो symbol है, you just add this symbol before that operation. So if you do something like this, R1 multiplied by R2, this would try to find out the scalar or dot product of these two vectors R1 and R2. However, if you say R1 dot and then multiplied by R2, so you are trying to do element by element multiplication. You are basically asking Octave to multiply the corresponding elements of these two row vectors, or if they are column vectors, to multiply the corresponding elements of those column vectors. Okay, so you want to do that. So this will not result in a scalar value. This will result in a vector of the same order, a row vector of the same size, and the entries of that row vector will be basically uh, the product of the corresponding entries in these two row vectors. Okay, so you can do that. So this gives you this particular vector as an output. So what happened here? You just multiplied the corresponding entries. Okay, so at times this is what you need to do, and you can do it for matrices as well. For example, let us create two matrices. Say we have M1. So M1 equal to, say for example, we want to generate it using random values. Maximum value is 5 and its size is 2 by 2, say for example. So this is M1. So let's say we want to have M2. M2 is also the same thing. A matrix with random values in the range of 1 to 5. Okay. Now if you do this M1 multiplied by M2, this will do the matrix multiplication. First, the row vector 1, 3 would be multiplied with the column vector 4, 1. Then the row vector 1, 3 will be multiplied with the column vector 2, 3. Then 2, 1 will be multiplied with 4, 1. Then 2, 1 will be multiplied by 2, 3. So this would give you this particular result. However, you can also do an element by element multiplication. Like just multiply the corresponding elements. 1 4s are 4, 3 2s are 6, 2 1s are 1, and 1 3s are 3. Okay, so you'll get 4, 6, 2, 3. That would be the element by element multiplication. How can you do that? You just add this period symbol before multiplication. So that will tell Octave that you don't want to do the typical matrix multiplication, the standard matrix multiplication. You just want the element by element multiplication. Of course, for that they need to be conformant here, like the number of elements, the number of rows and columns in both these matrices should be the same, but it would give you a totally different result. So why? Because this is element-wise multiplication. Okay? So if you do the element-wise multiplication, so you are multiplying these matrices element by element. 1 4s are 4. Okay, 1 4s are 4, and then uh, 2 1s are 2, 1 3s are 3, and here we have 2 and there we have 3, so 3 2s are 6. So you get this result. Okay, so MATLAB and Octave, they give you this option of performing element-wise operations. That does not make any difference in the case of addition and subtraction, but it does make a lot of difference in the case of multiplication and exponentiation. Okay, so exponentiation is also another very tricky operation. Not tricky, but in the case of vectors and matrices, it can get a little bit tricky. So let us clear the command window. Let me have this vector r1. So this is vector r1, say for example. And if we say r1 raised to the power 2, so I want to find the square of r1. Can I do that? Okay. So I cannot do that. Like this operation, exponentiation is not as such defined for vectors or matrices. What I can do is element-wise exponentiation. I can tell Octave that just do element-wise exponentiation of R1. Like this would tell Octave find the square of each element of this vector R1. Okay. So just by putting this dot before exponentiation, you can correct this situation. And now it will find you the exponent of each element of R1. Okay. So what did you get? You got the square of each element of R1. 1 ka square is 1, 2 square is 4, 3 square is 9, and then 4 square is 16. Similarly, you can do this thing as well. Like you can treat R1 as a vector of exponents. You can treat R1 as a vector of exponents. So you can say, you can have a scalar value, say 2, and you can say 2 raised to the power R1. Okay. So now what will happen is, again, and we are doing element-wise exponentiation, what will happen is Octave will treat R1 as a vector of exponents. So it's not just one exponent. Like if we do 2 raised to the power 3, it will just find 2 raised to the power 3. But here it will treat R1 as a vector of exponents. Okay. So it will find 2 raised to the power 1, 2 raised to the power 2, 2 raised to the power 3, and 2 raised to the power 4. Okay. When you press enter, you will get 2, 4, 8, 16. So now R1 is being treated as a vector of exponents. And similarly, like we have, say, R1, this is R1, and this is R2. Let us say we want to do R1. Let us try whether we can do this or not. R1 raised to the power, say, R2. Okay. So we want the corresponding elements of R1 raised to the power, which would be the corresponding element in R2. Can we do that? Does it make any sense? Yes. Yes, it does. Okay, so we can do that. We can find the uh, element-wise, one vector would have the bases and the other vector would have the exponents. So element by element exponentiation can also be done. So 1 raised to power 1 is 1, 2 raised to power 0 is 1, 3 raised to power 0 is 1, 4 raised to power 5 is 1024. And you can do it the other way around as well. You can say R2 raised to the power R1. Okay? So you can do something like that as well. Now 1 raised to the power 1 is 1, 0 raised to power 2 is 0, 0 raised to power 3 is 0, 5 raised to power 4, that will give you some number, 625. Okay, so you can do it this way as well. So element-wise operation, this is also important, especially when you are doing multiplication, division, and exponentiation. So I showed it for you in the case of multiplication and exponentiation, but it also applies to division as well. Element-wise operation, it also applies to division as well. And how do you do element-wise operation? So you do this by using this dot along with the operator. Okay, so you use the dot or the period sign along with the operator, exponentiation or multiplication or division. Okay, so you can do that as well. So I hope you know the difference between normal multiplication of vectors and matrices and this element-wise multiplication. I hope you know the difference. The next topic that we want to talk about is relational operator, and after that we will learn how to do script programming. So you have seen relational operators in action. Let us do that again. Let me clear the command window. Let us clear the workspace. So what are relational operators? Relational operators basically tell you the relationship between two values. Those values can be constants. Like this is a constant value. 45 is a constant value. It is not a variable. So you can say, is 45 less than 30? So the answer would be yes, 1. Okay, so we are comparing two constants. You can compare two variables as well. Say A has the value, let us say A has some value 625 and B has this value 230, say for example. And you can ask this question, is A less than B? So the answer would be no, 0. You can say, is A greater than B? Yes, 1. Is A equal to B? No. Okay. Is A not equal to B? Yes, A and B are not equal. Is A less than or equal to B? No, 625 is neither less nor equal to B. Is A greater than or equal to B? Yes. Okay. So you can do these are all relational operators. Whenever you use a relational operator, you always get a logical output. Logical output is either yes or no, true or false, 1 or 0. 1 is true, 0 is false. Okay. So the answer that you get, it is logical. Its type is logical. Okay. So logical means it is either true or false. Okay. Now you can, this is a constant value. Here we compare two constants. Here we are comparing two variables. You can compare a variable and a constant. You can do all sorts of things. For example, you can say, is A greater than 1000? So the answer is no. Is A less than 1000? So the answer would be yes, true. Okay. So here we compared a variable and a constant. You can do that. Okay. Let me clear the workspace and let me clear the command window. Let us create a vector A, and let's say A has these values 4, 3, 8, 1, say for example, and let's say we have another vector of the same order, and it has these values 1, 8, 9, 3, say for example. Okay. So we have vector A and we have vector B, and let's say we want to use the relational operators with these vectors now. So what are we going to get? We want to ask, is vector A less than vector B? Now, this less than operation is not defined for vectors. Like, what do we mean by even this comparison? Like, a vector A is less than vector B. Are we comparing its magnitude or what? So, like, it's not clearly defined for vectors. But how would Octave interpret or execute this particular command? So Octave will basically think that you want to compare A and B element by element. So it will do a comparison of vector A and B element by element. So it will first check, is 4 less than 1? Answer would be no. So it will put a 0 in the answer. Is 3 less than 8? Answer is yes, a 1 here. Is 8 less than 9? Answer is yes, a 1 here. Is 1 less than 3? Answer is yes, so a 1 here. So you'll get 0, 1, 1, 1. That you will get a vector of logical values as answers. Okay, so we get a vector of logical values. This shows the comparison of the first elements of A and B. Second element, this shows the result of the comparison of the second elements of A and B. This shows the comparison of the elements at index number 3 in A and B. And this shows the comparison result of elements at index number 1 of A and B. Similarly, if you say, is A greater than B, okay, so you're going to get this result 1, 0, 0. So this statement is true for the first elements at index number 1, and for all the remaining elements this statement is false. So you'll get 1, 0, 0. You can say, is A equal to B? Okay, so you'll get 0 zeros, all zeros. Is A not equal to B? All ones, because it's true, all the elements of A and B at all these indexes, they are not equal to each other. Okay, so this again is true. Similarly, you can use all those other relational operators. A is less than or equal to B. Okay, it will return you the same result, 1, 0, 1, 1. Similarly, you can say, is A greater than or equal to B? So it will return you 1, 0, 0, 0. Okay, so you can use these relation operators with vectors as well, and it will basically how these relational operators will work. They will basically compare those vectors element by element and return you a vector of logical values as a result, and each result in that vector of logical values will basically show the comparison of the corresponding elements in those two vectors. The same applies for matrices as well. If you create matrices of the same size and you compare those matrices using these relational operators, so you will get a matrix of logical values as a result. Okay, so let us do that as an example. Let me clear the workspace and let me clear the command window. Let us create these two matrices M1. So M1 would be a matrix of random integer values in the range of 1 to say 8, and its size would be 4 by 4. So this is say M1. And let us create M2. So it again is in the range of 8 and its size is 4 by 4. Okay, this is M2. Now let us compare the two. Okay, so is M1 equal to M2? No. At some places no, at some places yes. For example, 4 and 4 these are equal, 3 and 3 these are equal, 4 and 4 here this is also equal. So it will basically compare element by element and give you the result. So only 1, 2, 3 entries are equal, the rest are unequal. So if you do this inequality test, is M1 not equal to M2? So it will have 3 zeros and all the other ones. Okay, so you can see how it works. Similarly, you can do all those other relational operators. Is M1 less than M2? Okay, so you get this. You can do a comparison of corresponding elements of M1 and M2, and I'm sure you'll end up with the same logical matrix. So the point that I want to make is that you can use the relational operators not just with constants and scalars, but you can also use it with vectors of the same size and matrices of the same dimensions. Okay, and the result would be a vector of logical values or a matrix of logical values, and each value in that vector would basically show the result of comparison between the corresponding elements in those vectors or matrices. Okay, so I hope this part is also clear. The last part for this particular lecture that we want to talk about is programming using script files. Let's see if we have enough time for that. I guess we have. We can talk about that. So we'll try a very simple. Up until now, like we have been using these commands. We have been entering commands at the command window, and then we have been executing every single command. So a script file is basically a text file that contains multiple Octave commands, and you put those commands in a script file, and that those set of commands they do something specific. Okay, so say for example we want to do something that we have already done, but we'll do it in a script file. Say we want to plot a sine wave and we want to plot multiple cycles of that sine wave. Okay, so we want to do that using a script file. So how can you do that in a script file? So you can create a script file. Let me again clear the workspace and let us clear the command window. You can create a script file by clicking here on this button in the toolbar. It says, the screen tip says new script. So you can click here and a new script file will be created. So the editor opens up. This script file that we just created, it is unnamed. It does not have any name. You can save it for the first time, and when you save it, you will give it a name. So it is always a very good idea that you save whatever file you create, so you should always save it. So let us save it. You can use the shortcut Control plus S, or you can just simply say save. You have the save button available here as well. So we want this file to be saved in a directory that we created for Octave. Okay, so this inside Octave, let us create another folder. Let us name that folder as scripts. So these are Octave scripts, and this is let us name this script. Let us give it a meaningful name. So we want to plot cycles of sine wave. So let us call it sine waves. We want to plot sine waves, multiple sine waves. Okay. Okay, save. So we have saved the file. We haven't written any code yet, but we have saved it. Okay, so now whatever we write and when we press Control plus S, so it will be saved automatically. The font size would be a little small. Okay, so say for example, if we want to plot a sine wave, what do we need to do? We need to first generate angles, and then we need to find sine of those angles, and then we need to plot the two. Okay, that is what we need to do. Here we want to print the number of cycles of sine wave. So you can have a variable in which you store cycles. Okay, so say for example we will have a variable cycles, and in the variable cycles we specify, say initially we want 5 cycles of the sine wave. Okay, and after I write a statement I put this semicolon because I don't want any output to be generated on the command window unless I want that output. Okay, so first of all, like the purpose of this script is that we want to plot multiple cycles of a sine wave. So I have declared a variable that stores the number of cycles, 5. Okay. Next, we want to generate angle values for those cycles. Angle values for those cycles. Okay. So before we do that, if you see like the font size is small here, I want all of you to be able to see it. So we can go to the edit menu and we can go to preferences and we can edit our preferences. So in those preferences, we can go to the editor and select a different font size, a slightly bigger font size, okay, so that you can see things clearly. So this is our editor, and let's see. Okay, here. So the font size here is 10. Okay, Octave default font size is 12. So let us increase it to say 16. Okay, so I hope that would be enough. Default command keyword operator. Okay, so let's do that. Apply. It does take a little bit of time, but let's be a little patient. Okay, so now the font size has increased a little bit. Okay, I hope this is clear to you. You can see it clearly. So the next thing that we need to do, we need to generate angles for 5 cycles. Now angles is going to be a vector. Okay, so angle. Oh, okay. Okay, I don't know what happened. You're back here, but let's see. Let us give it some time so that this window goes away. And okay, so let's get back here. So we want to generate angles for 4 cycles. Okay, angles for 4 cycles. Now the angles, how do you want these angles to be? In radians or in degrees? So say for example we want the angles to be in radians. Okay, and how do you want, like you can use the comprehension, the colon operator to generate these angles, or you can use the linear space function. So let's use the linear space function. And in the linear space function, you specify the range, like we want the angle to start from 0. We want it to go to, if it goes from 0 to 2 pi, that would be 1 cycle. Okay, but we are not interested in just having 1 cycle. We are interested in having cycles, number of cycles. Okay, so right now cycles has the value 5, so we want as many cycles as the user wants. Okay, so we want the angle to start from 0 and we don't want it to go up until 2 pi. That would be just 1 cycle. Okay, so we want this to go up until as many cycles as we want. So how many cycles do we want? So that information is stored in the variable cycles. So we want cycles to be multiplied with 2 pi. So if cycle has 5, so we want it to go from 0 to 10 pi. That would be 5 cycles. If cycles is say 50, so we want it to go from 0 to 50 pi. Sorry, 100 pi. Okay, 50 multiplied by 2 pi. So that is the final value that we want to have. And how many points do we want to have? Okay, so say for example we want to have you can specify a certain number of points, a fixed number of points, 100 points, 200 points. You can do that, or you can link it to the number of cycles. So say for example we want to have 30 points per cycle. Okay, so you can do that. You can say the number of points that we want is 30 multiplied by cycles. So if we have one cycle, so we will have just 30 points, 30 elements in the angles vector. If we have two cycles, we will have 60. If we have 10 cycles, we will have 300 points. Okay, so as the number of cycles increases, the number of angle values in the vector angles, that would also increase. Okay, so far so good. Now we need to find out the sine of these angles. So that is again very simple. So we need to find the sine values, and sine values of what? Sine values of these angles. Okay, angles. Oh, okay. So we have the angles, we have their sine values. Now we can plot these two. So you can simply say plot. Okay, it's no different. Script programming is no different than writing these commands on the command window. They are more or less the same. But what you do here is you put all those commands together in one file, and when you execute it, so all these commands are executed in a sequence together, and you see the output. Okay, so you don't have to it is not that interactive. It is just a batch of commands put together and executed in just one go. So we want angles to be on the x-axis, and we want the sine values to be on the y-axis. This is what we want. Okay, so once you are done, once you have written your code, then you might want to run it, and you can run it in two different ways. One is you go to the run menu here, and you say save file and run. It will ask you that you're not currently in the scripts directory where this script file is stored. So do you want to go there? Yes, change directory. So now we are in the scripts directory, and we can see the sine waves.m, the script file. So these are 50 cycles of sine wave. Okay, these are 50 cycles of sine wave. Maybe they're not that clear. These are a lot. So let us reduce them. Say we want just 10 cycles. Okay, so let us save and run this file again. So these are 10 cycles of sine wave. 10 cycles of the sine wave. Okay, so you change the number of cycles here, and you don't have to do anything or change anything in the rest of the code. You just change the number of cycles, and you get as many cycles as you want. Okay, so say we want 5 cycles. So now we have 5 cycles of the sine wave. Okay. Similarly, once you have the sine wave, you can also find the cosine. You can also have the cosine wave side by side. Cos values is equal to cos of angles. Okay, so now you have both the sine and cos values. You have plotted the sine wave, and now you want to plot the cosine wave as well side by side. So do a hold on and plot the cosine wave as well, angles comma cos values, and then after that you can do a hold off. Okay, so now you will have two waves together, cosine and sine waves. Okay, 5 cycles of each of these waves, so you can have it. So this is how script programming works. Okay, so this was basically an introduction to it. In the next lecture, two lectures, which I'll upload today, inshallah, we will look at more examples of script programming. Okay, so this is how you do it, and there are other videos that are already uploaded in the on YouTube. You can go through those videos and you can learn more about script programming by looking at some interesting examples. I hope this would be enough for this session. So let us stop it and see you in the next session.